Let's look at two other factors that affect ventilation. First being resistance in the airways, and then lung compliance. Now remember, when we change from the bronchi areas to the bronchiole areas, we lose the cartilage, but we have smooth muscle surrounding these ligaments, which what that's going to end up doing, or when I say ligaments, I meant elastic fibers, but what the smooth muscle is going to end up doing is being able to contract, which is going to affect the diameter of the airways. So obviously, if there's air molecules coming through here, then we can create resistance, or we can counter the resistance. And of course, we create resistance if we shrink our diameter, and we take away resistance when we increase our diameter. So if a bronchiole constricts due to something like our parasympathetic nervous system, or excuse me, our something like an allergen or something like a histamine, triggering our smooth muscle here to constrict. If that does constrict, then it's going to increase the resistance to the amount of air molecules, because they have less space and they can literally bump into the sides of the walls. So it would increase their resistance. Here we see the decreasing in the diameter, and we see how the air molecules have less space to travel in. Therefore, there's more friction between them and the walls. So we can say airflow is equal to pressure divided by the resistance. And resistance, of course, being primarily determined by, what's the diameter of the walls, and are our smooth muscles contracting or not. So in healthy lungs, as this says, there's usually little resistance to the air, so air flows easily in and out of the lungs. Okay, so here we have a parasympathetic nerve. We have epinephrine, which is released from our adrenal glands. Here we have the histamines that are, the inflammatory mediators that we talked about. Okay, so parasympathetic is actually going to release acetylcholine, which is going to then allow, basically, keep the muscles somewhat contracted and keep the smaller. Now, when we're in a rest and digest parasympathetic state, then, we don't need to take in as much air as if we're exercising or in an emergency. So it's okay to keep this partially contracted. If we came across an allergen, such as, pollen or something like that, or something we're allergic to, then histamines will actually also cause these smooth muscles to constrict, and that will then make the smaller, increasing the resistance. Well, why would we want that to happen? Well, if we're coming in contact through our breathing with something that we're allergic to or that our body doesn't want, it's going to try to restrict how much of it is coming inside of it. Therefore, histamines would cause this to constrict. On the other hand, if we're in an emergency and epinephrine or adrenaline is released, we want our airways as big as possible, so therefore the epinephrine is actually going to cause the smooth muscles to relax, cause our airways to get bigger so we can get more air into them. Okay, we know part of our lung tissue is made up of elastic fibers, which makes the lungs able to expand and be flexible. But if you have certain diseases that harden that elasticity instead of allowing it to expand, then you won't be able to inflate your lungs as easily, and that will definitely affect, how large they can become, and even how small they can become, and how easy it is for air to go in and out of them. So one thing about lung compliance, or how easily it expands, is the elastic fibers. But the other thing is the alveoli surface tension, which is created by that very important moist layer of water that's always within the alveoli, but the fact that it's not pure water, that it is broken up with surfactant. Because if it were pure water, the alveoli would totally collapse. Here we see a single alveolus out of the millions that we have. Again, we've got the epithelial cells inside, we have the macrophages, the alveolar macrophages that patrol it, but we've also got these surfactant secreting cells. Now notice we got this alveolar fluid, which is mostly water, but the surfactant secreting cells actually secrete a lipoprotein that breaks up those hydrogen bonds between the cells. So instead of totally collapsing, they only partially collapse when air leaves them, and they reinflate very easily. If they totally collapse, because we just had water due to the hydrogen bonds pulling on the water molecules, if we totally collapsed, it would take way too much energy to reinflate it every time we inhaled. So having this surfactant secreting cells and having the surfactant release that helps break up those tension bonds, the same bonds that allow us to skip rocks across water. And when we break those bonds up, then we can still keep a moist layer on the lungs, but not have to totally re-inflate it. Now remember, it has to be an extremely thin layer because we've got to be able to diffuse oxygen through that layer into the blood, into the capillaries that are embedded in the alveoli. Okay, premature infants, remember, they don't take their first breath till they're born, and if they're premature and they haven't had a chance to develop the surfactant, then sometimes they have to have an artificial surfactant introduced into their lungs so they do have the ability to breathe. Here we actually see an alveolus totally collapsed because it didn't have the surfactant to break up the surface tension between the water molecules. And again, we don't have enough energy to totally reinflate every alveoli, so we wouldn't be able to survive very long if we didn't have a surfactant introduced into that very thin layer, so we can keep our alveoli inflated and they can partially collapse, not totally collapse. In infants without the necessary amount of surfactant, it's called respiratory distress syndrome of the newborn, and again, we would have to introduce an artificial surfactant to keep the alveoli from totally collapsing. Okay, the next major topic is gas exchange, because we know that air is made up of different gases, and we're primarily trying to bring oxygen into the blood so we can deliver it to our cells. And we're primarily trying to take carbon dioxide that was a waste product of the cellular respiration. We're trying to get that away from the body, so we're delivering the carbon dioxide to the lungs to exhale it. We're delivering the oxygen from the lungs to the blood to get it to our tissues. So in our picture here, these are alveoli over here. This is our lungs. Oxygen's coming in, going into our bloodstream. Carbon dioxide is leaving. This is a pulmonary capillary. Remember our pulmonary arteries and pulmonary veins? They branch down into the pulmonary capillaries. Remember, arteries take blood away from the heart, so pulmonary artery is going to be oxygen poor. Pulmonary vein is going to pick up the oxygen-rich blood, take it back to the left side of the heart. So here around the lungs, these are the capillaries that are next to the alveoli in this area where we have the simple squamous cell of the capillary and the simple squamous cell of the alveolus, and the basement membrane between them extremely small, so our air molecules can diffuse across them. That's our respiratory membrane, and we have that very thin surfactant fluid of water and surfactant on the other side of that. That has to be very thin, because if it becomes too thick, we can't trade the air molecules across it. Okay, just what is air made up of? Well, air is made up of several different individual gases. And the combination of those gases, each gas has what we call a partial pressure. Because air is several things, then part of the air is a partial pressure of whatever is making up the whole thing. Now notice here we've got atmospheric pressure, because we are here at sea level. We've got atmospheric pressure of 760. So that means the percentage of my different air molecules and the pressure created by that percentage has to equal 760. So you might think that oxygen is the biggest percentage, but in reality, nitrogen is the biggest percentage of air. So when you're breathing in air, you're breathing in more nitrogen than you are oxygen, but yet your body is using the oxygen for specific things, and the nitrogen has what we call a low solubility, which we'll explain a little bit later. Okay. So now we see that oxygen makes up 20.9% of the 760. Carbon dioxide, what we're inhaling, only makes up 0.04% of the 760, whereas nitrogen by far makes up, more than 3/4 of the air that we're breathing in, 78.6%. And then the water that's in the air is only about 0.46. So obviously this is what is the biggest component of air. This is the second biggest component of air, then this, and then finally carbon dioxide. Now when I take the percentage that's always in air, it doesn't matter where I'm at. Here I happen to be at sea level. That's my baseline unit for atmospheric pressure. But that number can change. But the percentages on Earth will not change for the most part. Now, so 20.9% of 760 is 159. My partial pressure is 159 millimeters of mercury of the oxygen I breathed in. Whereas the partial pressure of the carbon dioxide I breathed in is only 0.3%. Or excuse me, 0.3 millimeters of mercury, whereas out of the 760, then nitrogen by far made up the majority of the partial pressure of the air that I breathed in, 597 out of 760, which was 78.6% of it. And then water made up 3.5 millimeters of mercury, which was 0.46% of 760. But these are the four gases that are in air, and then when you see that big P beside of it, that's saying we're talking about that partial pressure of that gas of all the air. Well, we talked about Boyle's law, about the inverse relationship between pressure and volume. Now we're looking at Dalton's law, saying that in a mixture of gases, which that's a mixture of gases, the total pressure, which in this case is 760, is the sum, it's all this
in the total gas mixture.
It's the sum of each of these gases. Okay, so that's just kind of straightforward. Now notice here, we're actually on Mount Whitney, which is 14,495, so we're not at sea level anymore, so our atmospheric pressure has dropped quite a bit, but our percentages still remain the same. We still have 20.9% of the air is oxygen, 78.6% is still nitrogen, even though the overall atmospheric pressure has dropped because we're so high in elevation. And of course that explains why you struggle breathing when you go up in elevation. Now again, just like the atmospheric pressure drops, well, the percentage of that is going to be much lower than the percentage of 760. Therefore, I'm only going to have a partial pressure of 92 millimeters of mercury of oxygen when I'm standing on this mountain versus if I'm standing on the beach. So I probably have a lot better chance running a distance on the beach than I would try to run up here because I'm not going to get near as many oxygen molecules. Now there are athletes who actually train at high elevations because there's less oxygen and it will trigger the body to actually make more red blood cells. So if they train at a high elevation, their body says, oh, there's low oxygen, I better make more red blood cells. Then they can go compete at a lower elevation and they will have more red blood cells to compete with. There's even people who will save the blood when they do this training and then re-inject it when they go compete, and that's called blood.
At high altitudes.
That's called blood doping, and that's illegal. Okay, now we're going to talk about another really important law, Henry's law, and a really important concept about solubility and how the different gases in air act differently when they're going from one medium into another. In other words, when they're crossing from air into fluid, and if you imagine, the alveoli have air in them or space in them, and they got to travel from the space in the alveoli through the little bit of the lining of the fluid through the surfaces into the plasma of the blood. So that's what this is going to talk about. It's going to talk about how oxygen and carbon dioxide and nitrogen all have different solubilities, all have different abilities to cross from space into a fluid. Okay, so the amount of gas which dissolves in a liquid is proportional to two things: the partial pressure of the gas. Remember, we put the big P in front of the different gases, and we know that nitrogen had a totally different partial pressure than oxygen did. Oxygen had a totally different partial pressure than carbon dioxide did. But then the next factor is the solubility of the gas. In other words, how easy does the gas travel from one medium like air into another medium like liquid?